All right, ready? Oops, yeah, I'm recording this. Now with this weather, it's kind of cold outside. And so I know a number of people are having trouble getting here and stuff like that. So I'm glad those of you who can made it today. I always think I don't mind this time of winter because I always think it's the end of January kind of, and it's really cold, and so it can only get better from here. This is right. This is cold as it gets. Here, this is bad. This is winter in Minnesota, and it should get warmer soon. Okay, we'll probably have another week of sub-zero weather, but I mean, by and large, we've peaked. We've hit the low, and now it'll get warmer going forward here. So it's all uphill from here. Down. I don't know what the right metaphor for. It's all warmer from here, hopefully. One week. Uh, okay. So it's Tuesday, second week. So we start unit 2. We'll be going over the textbook material, talking about some new stuff today here. We'll be working on the exercise in class today, get you working on that. So hopefully by the end of the day, you'll have done the exercise. Remember, you have the activity. This is something you can do outside of class. One thing that we want to bring into this class as far as architecture goes is what is called cloud architecture. A lot of the hardware that you'll use these days is actually not physical hardware, but hardware that's out in the cloud in some data center somewhere else. Most of the books, that are out there don't cover cloud hardware. And so what I've done in this course is we've gone through and added a number of units, particularly using the main cloud vendors out there and working with them. And they have their free training, and we'll do that. We will bring this into some of the labs later on. In fact, there's a whole chapter of a textbook on virtual machines, that sort of stuff. And so we will do some cloud stuff more in the labs and later on, but this beginning stuff, it'll seem kind of separate. So right now we'll be doing physical hardware and cloud stuff. The cloud stuff will be kind of in your activities, and the physical stuff will be in the labs. And then, after about 5 weeks, they'll start merging together, and we'll see them more related there. But I'll just warn you that a lot of this cloud stuff will seem kind of like, why is that in this course right now? And you'll be wondering that. So, and again, you can choose. I would suggest you choose kind of one cloud vendor to start working with, and just you can swap back and forth. But I think it's sometimes nice to just pick one of the vendors: Google Cloud, Microsoft Azure, Amazon, AWS, and just follow through their learning paths here and see how that goes. Some of them will be part of larger courses. So like the Google one we're starting, there's this Google Cloud Essentials course. We'll do, over the next few weeks, a couple parts of that here. And you can work through. And so some of this is part of a bigger course sort of stuff. Some of them are standalone. I mean, they're all kind of standalone units, but sometimes, because sometimes some students like to be able to say when you're done, rather than just I did a couple online tutorials, but say I've completed the Google Cloud Essentials online course or something like that. So we can, and again, all 3 of these will have similar stuff. In fact, I think next unit, we'll start more particular, like we'll start a 3-week series with Microsoft where you can do the Azure stuff, and then the future ones will be, actually this will be over 4 weeks. We'll do most of the, I think we'll do 3 of the 4 of these, and then if you want, you can do one on your own. Similar here, we'll do a couple of those, and Amazon, we'll start the Amazon AWS Cloud Practitioner Essentials course. And again, we'll do about 2 units a week. And again, I would just pick one of these. And again, you can jump back and forth, but pick one of these that you're interested in and work on that. So, uh, so let's jump into the, oh yeah, and then the lab will of course be on Thursday. Remember, if you have your hardware that we've got some more equipment that came in the mail on Sunday. So I think I have parts now for everything. I fixed a couple of the computers. So I think hopefully we'll have, our goal is to have everything working on Thursday for our lab. So, okay, let's jump into the readings here. So in a normal, like in an advanced graduate school architecture course, you'd start from actual digital, analog components like little resistors and capacitors, and you'd slowly build up a whole computer by parts. And we're kind of look at that now, and I think that's really a cool way to kind of see things like how you know what a computer is, and you know it uses binary and stuff like that a little bit, but what does that actually mean from a hardware point of view, and how do you build a computer from inside? So we're actually starting that journey today, looking at how we create digital logic. So we say computers are digital. What do we mean by that? And how do we create these digital circuits there? There aren't generally digital components. I mean, electricity isn't digital. Electricity is analog. And so how do we make it digital? And that's what we're doing today. And then we'll start in the next couple of weeks, we'll start with that. And then we'll start building parts of it. So like when we get to memory, how do we build memory out of the parts that we know how to do? So we'll make primitive parts today, and we'll use those to make more advanced parts in future weeks. So hopefully we'll see this kind of go together. So let's jump into chapter 2 of the textbook here. Please, okay. So we're looking at digital logic. And again, what we're trying to really do is build these things. So we'll talk about what a transistor is, and we'll build logic gates. We're not going to get into latches and flip-flops and registers yet. That'll be when we get to memory. So we'll start the first part of this unit. In fact, I think this says we're doing pages 27 to 34, stop at latches. So we're going to go up and not do latch, or we might just look at latches, but that's where we start getting into memory and stuff. We'll do that. And then later on, so this will be in our future units when we do memory, we'll do latches, flip-flops, and registers. And then when we get to processors, we'll talk about adders and clocking and things like that. So we'll just get started on this unit here. So I never know how much you know about electricity, and did you do any electricity in middle school or computer or high school labs? Or did you do it at home at all? So let's just talk about some basic concepts here. So we will measure different components and different things. So there's something called electrical current that's flowing around, and we often measure that in amps, and that's kind of the flow rate. We often maybe a good visualization for electrical current is like water flowing through a pipe in a plumbing system. The current wants to flow through our wires similar ways, and we'll talk about that here. And amps will be kind of how fast the water is flowing through our pipes systems. We'll also talk about volts. The voltage will be kind of how much pressure is in that. So if this is a 3-volt system, it is pushing at very little pressure. It's kind of like if you have your faucet and you turned it on, you can turn on just a little bit. 3 volts will be a little bit of pressure going through. If you turn it up to like 5 volts, a little bit more, 12 volts, a lot of things run on, like your car battery runs at 12 volts and stuff like that. there. That's a little more pressure. You keep turning it up, it'll go higher and higher pressure or voltage. So the voltage is like how much it is pushing here. You can kind of imagine even like a stream of water flowing. The ampage is just the rate, how fast is the water flowing there. The voltage is how much, like if you were trying to stop that stream, how hard would it be to stop that stream? I remember being have you ever been, like, remember in the spring when everything melts and you go out to one of the state parks and one of the waterfalls and the water just flowing down so fast. It just like, so that's a lot of voltage here. What to watch, we'll be working with these large wires and stuff, and you can touch things and get shocks on here. Most of the stuff we're working with is pretty low voltage, 3 volts or 5 volts. Your like USB, like your phone charges with a USB charger, that's 5 volts generally here. And like a battery, a double-layered single, A battery, that's 1.5 volts. And then you probably can't even feel like you've touched both sides of a battery. It's so low voltage you don't even feel it going through your fingers. You don't get a shock from it compared. Now, like a 9-volt battery, those little square batteries, those you can kind of feel if you put your fingers on it there, put more sensitive part of your body on it, you can kind of feel the little voltage going across that. Other things like a car battery, 12-volt car battery, if you're touching that, you were definitely feeling that shock there. So the danger is a combination of the volts and the amps together here. So there's this relationship, volts equals amps times resistance. And again, resistance is like how hard it is to send our current through this circuit. And we will often have to add some resistance so that the current doesn't flow too freely through our stuff. One of the problems is that if the current flows too freely, it gets hot. It'll melt things. Hopefully, you can set up these things wrong so that if you set this up so there's no resistance and you're just sending current from like your power supply to ground through a wire, you can actually melt wire. I bet sometimes I do it regularly. You do something wrong and one of these, all of a sudden you smell this burnt rubber thing, and all of a sudden you notice one of your wires is starting to melt there. So again, we have to be careful a little bit of that with some of this stuff. And again, that's why we're often adding resistance, resistor into this area. So again, here's our basic circuit. We have symbols for the stuff. This symbol is supposed to represent like a battery or a voltage source here. And we have a positive and a negative, or sometimes called a ground side here. So in our circuits, we'll have certain pins that will be marked positive, either 3 volts or 5 volts, and other pins that are marked ground here, and that will be here. We'll also set up our boards here so that parts of them, one of the alleys will be positive and one of them will be marked negative, which will be ground here. This eye kind of shows the current. The current's going to start at our power supply or our battery and flow through our circuit and get over to here. And this is our resistance here that is doing. So this might be a resistor in our system, like we'll have actual physical, like here. This little thing here is a resistor. It just looks like a little bulb with our little plastic thing with lines, colored lines on it, and the colored lines will tell you how much resistance it has. But also every device, like if we were to put a motor in there or a light bulb or anything like that, will we'll have some resistance there for that. So there'll be, this is often whatever we're trying to make go or change or something like that for that here. So this is our basic configuration for this simple circuit. So right now, we can also try to measure the voltage at different places here and see where the voltage is here. Right now, because the wire is just, the current is just flowing here. If we measure like the voltage from here to here, again, I'm sure about my voltmeter. I have a next on Thursday, I'll bring a little voltmeter, which will have this. It'll be a little display, and then it'll have two wires. You can put one end on one side, one part of the circuit, another end on other part of the circuit, and it'll tell you how much voltage is between two parts of your circuit here. So again, with this resistor here, we can measure voltage from here to here, and or here to here, depending on different values here. Okay, the next thing we're going to talk about is a transistor here. And this really is a little device that made our digital computers possible. It is a switch, an electronic switch for this. So, and this is a one symbol for it here. What it shows is shows current coming in, going here, and then going out here. So this is the path from C to E is the path of current. Now B comes in here, and it should actually be like a little gap in here because it almost looks like the current coming in on C could go out B, and it isn't. There's a little gap here that keeps it. But B provides an on-off switch to this. So this is like a light switch. So just like here, so let's like we have our light switches here. So there's a wire coming into the light switch here, and then it's going out to the light and then coming back to ground. And so we can turn the lights off and on. So this is the little device here. Now, I have to manually turn this on and off. And there's a lot of switches that do that. So in fact, like we'll use some. This is a little switch that's a push button switch. I can click that. I can feel that push on and off to turn it on and off. So it might be big, it might be small, but these are physical switches here for this stuff. So that's this little switch right there. Now a transistor is an electronic switch there. Kind of reminds me, I have Alexa, and around our house, we replaced a bunch of our switches here with smart switches. So now I can tell Alexa to turn on the dining room lights or something like that because it's a smart switch. And so transistors are kind of like that in that if I provide a voltage here, it'll open up the switch. But if I don't provide a voltage, it's closed here. So C comes down and it's this, if there's no voltage on here, it'll stop here and not go on. If I apply a little voltage here, it'll go on further here. So I can use this to control if this goes on and off for that. So you can use one piece of electricity to control another part of electricity on or off here, which is really cool in a lot of ways. And again, there's lots of flexibility in that this B does not have to be at the same power or same current or voltage as the rest, as this supply current. So we can supply a little tiny voltage here on and off and control a much larger voltage here also and stuff like that. Okay, so once we have that, we're going to build up our logic gates here. So here's one of our logic gates we're going to try to build. So Here's our battery or our power supply. Current is flowing up here. Here's our resistor here. And here's our transistor. And it goes around here. Now, if we turn this on, if we provide a voltage here, our input, if we put some power here, that'll open this circuit and things will flow around. The current will flow around this circuit. If we don't provide any power here, this is closed, so things will flow and it'll stop here. So imagine this is a plumbing faucet. So here's our water pump here, and our water pressure is going here, going through this. And maybe this is, it's going through some parts of our plumbing system here. And then here, this is like our faucet. We can turn this on or off. And the question is, how much pressure, how much voltage is here? So if this is off, the voltage here is high because the water is pushing, the current is pushing, and it's all stuck here and trying to find somewhere to go. It can't go through this transistor because this is closed. And so if we provide an output here and open up, the current, the water would want to flow out here, here. So it would have a high voltage going out on this output. Now, if we were to open up this valve, this transistor, put a little voltage here, then the water is going to flow, the current is going to flow right through this. So now on our output here, the current is going to keep flowing right through here faster. And maybe there might be a little that trickles on the output. By and large, the output would be 0 there. So here, if we provide no input, 0 voltage here, the output will be 5 volts. And if we provide 5 volts here, the output will be basically 0 volts here. So it's the opposite here, the way this is structured. So with 2 resistors here and a transistor, we can create what we call a NOT gate, where the output here is the opposite of the input here. So now, and so this kind of walks you through this. We can build a little, what we call a truth table of this. So, and again, our inputs, now, the inputs are actually 0 volts and 5 volts. And actually, it's like 0.1 volts and 5 volts here, because it's not actually 0. It's just really low as the inputs and the outputs. And so the output, again, is, but rather than saying 5 volts or something like that, we just say 0 and 1. We just translate the actual voltage either on or off. So if it's very little, like 0, 0.1, 0.2, we'll just classify that 0. And if it's a voltage above 1, any like 5 volts, we'll classify it 1. So here's, if we have an input of 0, the output is 1. If the input is 1, the output is 0. That's how this. So that's our first digital logic gate. And we made it just with resistors and transistors idea. So these are all analog stuff, but we're able to create a digital gate with that. And this is the symbol we'll generally use for that here, the input and the output. Now we're going to do another one here. Similar to this, we've got, but we're going to have 2 inputs. We have a battery, we have 2 transistors here, and then we have our resistor, and then the completed circuit here. So if, so the question is, what is this output here? Here. So if we're getting current there, so if we turn these both on, the current will flow, the water would flow up here, it'll flow through this, assuming this is on, it'll flow through this, again, assuming this one's on too, and it'll go here. Now this resistor will make it harder for it to go this way. It can go this way, but it's harder. So it'll tend to want to go toward the output. So the output voltage will be high here. Now, if we stop this input, our water, our current will flow up this wire, over this wire, come, and then they'll stop. And we can't get down here. So then the output will be low. So we have to turn this on and this on to get the output here. So we need both of these on for the output to be high. So both of these have to be high for the output will be on. I don't know if you've ever, like in your house, you probably have three-way switches where like maybe on a stairway, if you turn one switch on, the light will go on. Or if you turn the other switch on, the light will go on there. And often it's with stairs or hallways, they'll have these two switches. I've tried to do those a lot, and what I typically do is wire them wrong. And so the wiring wrong means that they both have to be on. They both have to be up for them to be up. If one is down or the other is down, then the light's off there. And that's what we're basically saying here is that they both these switches have to be on because the wire has to go through here and through here to get down here. And that's what I said through here and through here. So we call that an AND gate. And here's our here's our possible inputs here. So we have two inputs now. We can have a 0 and a 0, a 1 and a 0, a 0 and a 1 and a 1 here. So again, they can both be off. The first one can be on and the second one will be off. The first one could be off and the second one will be on, or they could both be on. Now, of all those four combinations, which one will put voltage on the output? Only if they're both on here. So if they're both on, we get this. Otherwise, we get it's off here. So again, if this one's off, we're not getting the voltage over here. If this one's off, we're not getting the voltage here. If they're both off, we're certainly not getting the voltage here. The only way we get the voltage here if they're both on. So again, by wiring this, transistors and resistors, we can create this, and we use this symbol for it. This is our AND gate. And so we're making these digital gates. So far, we have a NOT gate and an AND gate for that sort of stuff. And again, if we look at this gate, we can look at the schematics. Here's our schematics. Here's our OR gate. Sorry, this was the AND gate. We can similarly do an OR gate here. And again, they're not going to show you this one so much. But you can wire it up similar to this. If you have both of them are off, then the output is 0. If one's on and the other one's off, then it turns on. If one's on, off, and the other one's on, it's on. Or if they're both on, they're on. So this is kind of like similar to almost like a three-way switch at your house. If one's on, it's on, or the other one's on. Kind of like that. Well, it's a little different because these are just on-off switches. So again, you can, as long as one of these switches is on, the light will be on here for this. And again, you can look up and you can wire this. You can create the same sort of stuff with just resistors and transistors sort of stuff. So we can have an AND gate and an OR gate and a NOT gate. And once we have those three gates, we can actually make all the other gates that we need for this stuff. So here's an XOR gate here. So it's off if they both match. If they're both off or they're both on, it's off. It's only on if one or the other is on. So if one or the other. So XOR, one or the other, but not both, is how we kind of think of that. So if one or the other is on, but not both, then we'll do it. And again, these are the symbols. So again, AND looks like a D, like in AND, I always think D. Or it looks like a Star Trek brand. I don't know quite how you remember it, but that's OR there. And then XOR is just like that, but we have an extra line in there to kind of mark it as XOR. You don't really have to memorize these. Just for the assignment today, we'll do this, but these won't be, we won't be using these every week or anything like that. But you might see circuit diagrams. I don't know. Yeah, I read, where, I don't know where you're going to see circuit diagrams or something like that, but you might see them at some point. I know that. So here we can wire up gates to do certain things, and we'll do symbols like this. So this is an AND gate. This is another AND gate. This is a NOT gate for this layout.
Man,
Let's take a peek at the assignment then, or I mean the exercise for this week. Let's see how far did I get to page 34. Yep, that was the end. Oh, good job. Okay, so I'm going to go back here. And I'm going to go to the exercise and open that up here. So again, just make a copy of this, do file, make copy, give it a name, and you'll want to submit this. Again, we'll do it today, you can, but it's not actually, you don't have to submit it till Sunday. I'll just warn you, every year, some student does them all in class and never submits them, loses points for submitting them late, and then remembers at the end of the semester that they haven't, I don't know. So just make sure you submit them. Even if you don't get them all right, submit it and see how you do. So, okay, so here's our values here. So let's see. And here's our things. Now, they have A, B, C, D, E here. You can write in which one is what here. So you can just put like this is a NOT gate here. So I could just write F there. I'd rather, I mean, if it were me, I would just write NOT there. As this first gate, invert input, and this is its symbol. So each one of these is supposed to match up with this diagram. They're not exactly perfect, but maybe if I actually put in an extra line there, I don't know if that's any better. So there. So again, fill in where each of these lines is, either the letter or the word up here, or both. I would provide one or the other, I guess. For what this symbol is over here. So yeah, fill those out here. Now, let's talk about this symbol. So an AND gate is like this, and it doesn't have a little circle up here. Here. So there's also, besides an AND gate, there's also the opposite of an AND gate, and we call that a not AND gate, and we don't like that. It's too many letters, so we say a NAND gate, a not AND gate, N-A-N-D gate there. So that would just make the opposite of this. So if this is our inputs, if it's the outputs, the output will be all flipped. Where there's a 1, there'd be a 0. Where there's a 0, there'd be a 1. It'd be the opposite of this. It's just like taking an and adding a not to it here. And so the symbol for that is this and with a little dot here, because the little dot comes from the NOT gate for this. So that's what you'll see. And similar with the OR gate. So what would you call a NOT OR? So the opposite of an OR would be a NOT OR. So we'll call that a NOR gate. Computer people are just so creative with their names and so lazy with, we can't say a NOT OR gate. We'll call it a NOR gate. That's much more interesting there. So that's what this is, a not AND gate. This is a not OR gate here. And we talked about the XOR, which is a little different. So Okay, I'm going to let this next part for a little bit, and I'm going to go down to part 3 and start talking about that. So on Thursdays, we'll start wiring up some wires here, and that's kind of fun sometimes, but it gets a little hard sometimes to do these wires and to get these wires correct. And so often when we design circuits, we'll use, well, not in this class, but professionals will use simulators to design the circuits initially there and lay out the circuit paths and stuff like that. So that's what we're going to use is a real simple simulator. So for part 3, we're going to create a simulator with this Logic.ly website. So I'm going to go to Logic.ly. It's going to suggest some more complicated things like latches and adders. We're not there yet. That'll be a couple weeks before. So you can just say close this. And here is our layout. Now, we can have buttons. We'll use this toggle button. And I'll just note that in some of this has changed this picture. So in some of the pictures online or in here, it'll be different. So here the switch is showing like this. That's slightly different to what's actually here. This is the new toggle switch here. So I'm going to want to build this sort of stuff. 2 switches, an AND gate, and a light bulb here. So I'm going to go here. I'm going to grab, and again, you should be able to just click, hold down, and drag these elements on the screen. So those are my 2 switches. And again, I don't want the push button. I want the toggle ones. And then I want to get an AND gate. Grab that and put it on the screen. And I want a light bulb here. And once you get those there, now there's these little circles here. And when you go over them, they get a little bigger. And when you do that, you can then run a wire and go to another one, and you'll see that get a little bigger, and you can drop it on there. So again, go over this till it gets a little bigger. And I click, drag, and I go here till it gets a little bigger, and it turns green in this case, and drag that wire. I want to drag from here to here. So now I can test out this light bulb here. I can try turning one on. It doesn't go on. I can try turning another on, and it goes on. And it'll kind of show the current in blue here. So I can see when I turn this on, the current flows to the AND gate, but doesn't go any further. But when I turn this one on, both of them are sending this blue current to the AND gate, and then it knows what AND goes, and it goes further here. So remember, our AND, what was the logic for an AND gate? That's what this was. And again, if they're both off, it's off. And again, same here, if they're both off, the light bulb's off. If one's on and the other's off, it's off. So I can do the same thing here. If one's on and the other off, it's off. And it's the other way around. If this one's off and this one's on, it's still off. And the only way it's on is if they're both on. So again, only way the light bulb's on is if they're both on. So that's what the AND is going to do. I forgot to make copies. I was changing this original one. I changed that back. Okay. So what do you need to do here for part 3? You want to create this layout. here, and you want to include some screen captures of at least two different combination of inputs. So like I could do this combination. Again, originally I was there's actually four combinations, but that's a lot. I think if you do two, that shows it. So again, you can, I don't know if you've done screen captures on Windows, but if you hold down the Windows key, the Shift key, and then press S for screen capture, it'll switch into the screen capture mode. You can just grab this, and then you can go back here and you can just paste it in here. So again, open this, turn on. I'm going to turn them both on so the light bulb's on. That'll be a nice one. And again, Windows, Shift, hold those both, and now hit S for screen capture. And then you can do this screen capture and paste that in here too. Now we can create different kinds of switches here. I can do a NOT gate here. You can ignore what's called the buffer. We're not going to be working with that. But I can put a NOT gate in here, see how that works. And again, connect this up if I want. Now the NOT will make it opposite here. So when these are off, it's off here, 0 here, and but the NOT will make it on here. So this will be set up so that this will, if these are off, this is off. I mean, this is on. So this is a NOT AND gate. And if I turn one on, it's still on. But when they're both on, this is off. So this is off when these are both on. If just one of them is off and one is on, this is on here. So this is an example of a NOT AND gate. I can actually replace it with an actual NOT AND gate. Let me see if I can delete this. Here's a NOT AND gate. You can see it's the AND gate with the little dot here. So it has part of an, it kind of shows symbolically that it's part on, part and part not. So I can do that. And again, if they're both on, this is off, one or the other, then it's going to be on. It's the opposite. It'll be the opposite of this. So you can try out different gates here. For the exercise, you want to do this one and then create a simulation of any other logic gate and try out the 4 combinations on the tip tables and include 2 of the pictures of the of 2 combinations. So again, this is, I could do this one or that. And again, you don't have to do NAND. You could do, if you want to just do OR. Where's my OR gate? Here's my OR gate. I could do that. And if one's on, it's on. If they're both on, they're on. If they're both, the only way to turn it off is if they're both off with the OR gate. Because that's, and we can see that in our little truth table here, or it's on, the output is 1 if they're both on, both ones, or if one is on and the other was off, or the vice versa. The only time it's 0 or off is when they're both off. So again, they're both off, this is off. If either one or the other is on, then, or they're both here, then it's on. Any questions? Is this making any sense? Is this making sense for ands and ors and nots? And from this, once we have ands and ors and nots, those three logic gates, we can make memory, we can make process, we can make adders, and so we'll make an add. We'll add part of a processor, add numbers together with just these gates, and we'll do like here. We're not going to go on to it till later, but this is what is called a latch, the primitive memory system with, again, these not, an or, and an and gate. And we'll make it actually a little more complicated latch here with a couple NAND gates and a NOT gate, so that we'll be able to store something in D, and the output will reflect it here. And then with E, we can reset, we can clear the memory there. So we'll talk about that. And then we'll make more complicated registers that'll store lots of things. So we'll build up these things, and we'll make more devices, and we'll make those into more complicated devices as we go. I'm going to jump ahead to the next chapter a little bit, and just talk a little bit about processors. So eventually we're going to be kind of making all the components for a processor. So let's just talk about what a processor is. This uses a simple processor called the 6502. Last week we talked a little bit about that. That's an old processor. It used to run the old video game systems and old computers. I don't think you probably have used any old computers, but maybe you've used an old Nintendo or something like that. Played a retro game somewhere, something like that. For this. So I'll talk about a simple processor made up of three main parts: what's called a control unit, arithmetic logic unit, ALU, and then a set of registers. So this is what a CPU is actually, what we will think of a CPU is made of. Computer is made of a control unit, an ALU, and some registers. Registers are memory that are very close to the processor, so they're very fast. We'll also add further away and slower some other bigger memory and some like input-output devices and stuff like that, other storage. But this, although it shows it right here, this is actually going to be very slow compared to like the registers, which will be very fast for that. So those are our parts of it. And we'll talk a little bit about a control unit and what it does. We'll talk more about memory and reading in things from memory for this. We'll start talking about a program counter, keeping track of this here, where we'll read in information into the program counter and process it, and how we want to update this here. So it talks about how a computer might be booted, some of this low-level stuff, and how we execute an instruction here for this. Now, some of this is we're going to get to later on in more detail, and some of it we're not going to get to too much. So the ALU, when we start thinking about ALU and building an adder, we'll do that, I think, in 2 weeks there. So we're just going to get the first part of this stuff done and just talk about it. One of the things I think you should have seen is the fetch execute cycle. And if you've had computer principles, you've seen the fetch execute cycle there. We'll execute it, or we'll fetch an instruction in from memory into a register. We'll then decode and run that instruction there. So we'll execute that instruction, and we'll fetch the next instruction, and then we'll execute that instruction there. This doesn't go over it very well. So, and again, some of you may not have had CS principles yet. So in the exercise, one thing I want you to do is watch this video or find a video of the fetch execute cycle here. Include some screenshot or something along that. It doesn't have to be a video, it can be an animation, it can be anything like that there. Maybe your social media, maybe you've been searching fetch, maybe it's just the algorithms are starting to feed you fetch execute cycles in your social media stuff. So if your feed has that, just do a screenshot of it, include that, or do a search on your favorite social media app of this. Maybe you're watching Tiff on tech and her great explanation of this hardware stuff there. I don't know who you're following. So YouTube has lots of videos. You can just find it. And again, there's lots of animations. You can find those. So again, I just need a screenshot of the animation or the video or something like that showing it. And just showing where it is. And I guess, did I say, and what you liked about that here, why you like that video. Okay, so that's part 4. Part 3 is this diagram with logically, we already kind of did. 1 was this matching thing. 2, where do you see this? So I don't know if you've done any programming yet here. Maybe have you done any programming yet? Is anyone in Java in programming 1? So some of you are in programming 1 or have had programming 1, so you've seen it. Some of you may not have had that yet. You may have seen programming. If nothing else, even in CS principles, you did some block programming. So the question is, where do we see these ands and nots there, and what symbols do we use? So in Java, particularly when we see if-then statements, in those sort of questions, we have Boolean expressions, and we use ampersand to mean and. So like we say, if x is less than 5 and x is less than 10, do this. We can use the or gates here, something or something, or we can do not is an exclamation point, not x less than 5 and x less than 10. So that's Java. Python, we actually write out the words and, or, and not here. Your job is to find out what are the logical operators in 2 other languages, C# and JavaScript. So do a quick search online, ask an AI or whatever, and I just want, so you'd say, in C# and is whatever, or is whatever, and not is what is used to define those. So do a search of C# and JavaScript. So if you were to name one language C# and the other language JavaScript, which one do you think would be more like Java? So it's not JavaScript. Oh, there. So, and here's one place we'll see it. C# will be very similar to Java. Okay, and then the rest of the class, you can either work on the exercise, get that all done, and if you want to work on one of these activities in class, you're fine. I'm gonna not talk anymore here. I'm gonna stop the recording, but I'll leave the Zoom up. If you guys get stuck anywhere, you can ask me here, but I'm just gonna pause recording because we're not